welcome back to the module 2 of this course, Ultrafast Optics and Spectroscopy. We are continuing this module, and what we have studied so far, different characteristics of ultrafast pulses using mathematical formulation. So, we will continue this module. So far, what we have seen that a short pulse can only be constructed using optical interference of plane waves. We will draw plane waves. We have one wave, plane wave like this, and we will consider slightly different frequency represented by different color. So, we are drawing two plane waves. They are interfering with each other. We will select one more color, one more frequency component. So, there are multiple frequency components we can consider, and what we see here is that at this point we have constructive interference. At this point we have constructive interference, and then there are points where we have destructive interference. So, this is going to be in phase, and this one is going to be out of phase. And due to this interference, what we are plotting here is this is the electric field and this is time. Similarly, the resultant field can be shown like this way. This dot line just to guide our eye. So, what we see is that the resultant field is varying like this way, which is nothing but a pulse. Now, this field variation will repeat after a certain time. Again, there will be in this position, there will be another pulse in time. And it will go on like this way. So, I am plotting here again resultant electric field due to this interference. And often we have pointed out that this field can be expressed, isolated pulse can be expressed as AT multiplied by e to the power I omega naught t minus k naught z. Here omega naught is the resultant or the average frequency component. I have so many frequency components. Let us say I have Avogadro number of frequency components. So, I get the average of it. On the other hand, this k naught is representing the average wave vector component, wave vector magnitude of the wave vector k1 plus k2 plus blah 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 divided by n, and n could be Avogadro number, which is 6 into 10 to the approximately 6 into 10 to the power 23. So, let us say I have this many numbers, 10 to the power 23 numbers of plane waves interfering with each other. If they are interfering with each other in time, we will have localized electromagnetic energy or the burst of electromagnetic energy. Each pulse can be expressed with the help of under SVEA, we can express by this equation. This is the equation representing an isolated pulse, not a pulse train. And omega naught is not a single frequency component, k naught is not associated with single frequency component. They are representing the average value of the frequency, angular frequency, and the wave vector. On the other hand, if we think about plane wave, one plane wave can be written as E, which is function of t, equals E naught e to the power I omega 1t minus k1z. So to avoid confusion, sometimes we also write like this way also, e to the power I omega naught t minus k naught z. When we write omega naught k1 for an plane wave, and when we write omega naught and k naught for pulse, we should remember that the meaning of this omega naught and k naught and omega naught and k naught in pulse are different. In the pulse, it is representing the average values, and in plane wave, it is representing its characteristic frequencies and the wave vector. So generally, to avoid this confusion, we generally use we do not use omega naught k naught z. We use omega 1 k1 z to represent plane wave. And for plane wave, it is single frequency component, and for a pulse, it is actually multiple frequency component. And this AT is the field envelope. This is called field envelope. How the modulation of the magnitude will occur. And this field envelope is nothing but this dotted line. So how this modulation will occur, that will be defined by this envelope function. So this envelope function, if we add this tip of this, then we get this envelope function, and this is represented by AT here. So what we have seen here, that interfering waves having slightly different frequencies produce pulse. The resultant field can then be represented by a pulse, which is nothing but localization of electromagnetic energy in time. Here, one can also argue that a pulse doesn't need to be always synthesized using optical method, which is interference. What we are showing here, in order to produce a pulse, I need many frequency components that we have shown. But one can argue that I really do not need many frequency components. I can use an electronic method. So this is an optical method to produce a pulse. But I can have electronic method as well. And in this method, what we can consider, I can write down a circuit. I have a source, then it is connected to a light source, and then I am using a switch, let's say. So if I have this circuit, then I can switch on and off. This is a switch, so I can make it on or off, and I'll assume that this is a light source, rather this is a monochromatic light source, let's say. It is very difficult to get monochromatic light source, but we'll consider that we have a monochromatic light source. Question is, with this configuration, can we prepare pulse? Can we synthesize pulse? Monochromatic, which means it gives only omega 1 frequency component, which means that I have only this ET equals E naught e to the power I omega 1t minus k1z whenever the circuit is on. So if I switch on and off, then as a function of time, if I plot everything, what I get is that a pulse, again a pulse, again a pulse, again a pulse, on off, like this way will continue, and we'll be able to control that. So this way we can actually create a pulse, and a temporal localization or temporarily localized burst of energy with single frequency omega 1 it can be synthesized using electronics. That's true. We can do that, but its pulse duration can be mostly microsecond. So the duration of the pulse can only be microsecond. It cannot be femtosecond. It cannot be femtosecond. It cannot be picosecond. It cannot be attosecond. It is not possible. The pulse duration is going to be microsecond. At best, it can be nanosecond. If it is not microsecond, if we can improve much, then it can be of the order of nanosecond, not less than nanosecond. It's because the response time of electronics is nanosecond. When we switch on and off, if we look at this pulse, it is nothing but I'm switching on and off. So this is 0 voltage. Suddenly I have something, then again certain value, and then I'm closing it. So the time by when I can switch on a particular device with an electronics, it is going to be nanosecond, because the response time of all electronics is going to be nanosecond, 10 to the power minus 9 second. It cannot be faster than a nanosecond. So the ultimate time resolution of this kind of idea, synthesizing of pulse, will depend on how quickly we can switch on and off. And the fastest time scale we can achieve with the help of electronics is going to be nanosecond. That's why the pulse duration at best we can produce with the help of this kind of methodology is going to be nanosecond pulses or microsecond pulses. In fact, electronically controlled flash lamp is used in the construction of nanosecond pulse laser such as ND-YAG laser. We can draw ND-YAG laser cavity here, and I'll draw the cavity to show you how this electronic approach is used. We need a cavity, optical cavity. We'll learn all this optical cavity very soon in this course. This optical cavity is prepared with the help of two mirrors facing each other, and then I have this lasing medium, which is nothing but ND-YAG rod. This ND-YAG rod is very common laser medium which we use in the synthesis of nanosecond pulses. And then this rod has to be excited, this medium has to be excited. We do this excitation with the help of a flash lamp, and this flash lamp is nothing but an electronically controlled flash lamp, and this is called flash lamp. A flash lamp, and in flash lamp what we do is this on and off. So basically it's flashing, but the time scale by which we can do this flash is going to be microsecond to nanosecond, and this is purely electronically controlled flash lamp. Electronically controlled flash lamp. So it is very important that we realize that a short pulse such as picosecond, femtosecond and attosecond can only be synthesized using optical interference method only. This is why often we say that an ultrafast laser cannot be externally triggered. See, if we think about this ND-YAG nanosecond laser, this can be externally triggered. Externally triggered, what does it mean? It means that I can operate this externally. I can operate this change of this on and off for this flash lamp externally or electronically, and then I can get the output. So I can trigger it externally, but ultrafast laser sources cannot be triggered externally, just because there is no electronics available currently which can trigger with that kind of time scale, femtosecond or picosecond time scale. It's way too slow. All electronics are way too slow for the ultrafast laser system. That's why we have to always use its internal trigger to externally trigger rest of the devices such as pulse, nozzle, counting electronics and etc. Ultrafast laser system cannot be triggered in the counting experiment. It cannot be triggered externally. It has to be triggered internally. So these are the concepts which we have already developed in this module. And this is the plane wave we are showing here. one plane wave propagating along z direction and one pulse propagating along z direction. Both are propagating along z direction. As pointed out previously, a plane wave will be represented by this equation, which is nothing but cosine modulated modulated oscillation. The real part of this is going to be in scalar quantity. It's going to be cos omega 1t minus k1z. This will express as 1, this will express as 1. To point out that this belongs to a plane wave. On the other hand, a pulse propagating along the z direction having similar kind of equation, except for this envelope function. This is called field envelope. It is associated with the field, and the average frequency component, I said previously that average frequency component is also called carrier wave. This is the average frequency component. Average frequency component, how do you get that? All the frequency components which are interfering, they will be summed and divided by its number, so that we get this average frequency component, and that's called carrier wave of a pulse. And field envelope is the modulation, the amplitude by which we will be able to modulate it. But this is under slowly varying envelope approximation, this expression suggesting that we have an isolated propagating pulse propagating along the z direction. Now the pulse here we are representing and also we have seen that in general the pulse to talk about the pulse, when we talk about the pulse, we also present its intensity profile, and intensity profile goes like this way. It is not exactly field envelope, it is slightly different from field envelope, because intensity is nothing but E star, which is nothing but AT square. So if AT is represented by a Gaussian function AT square minus AT square, then its intensity is going to be represented by minus 2 AT square. That's why we have the intensity profile inside the field envelope. It looks like this. It is here. Intensity profile would be always like this. If we consider the normalized, both functions normalized, then intensity profile is going to be like this, and its field envelope would like this. Its field envelope is like this. So their widths are little slightly different. And mostly we talk about intensity. In intensity profile, we should remember that there is no oscillation. It is just an envelope function, intensity envelope function. Now this pulse is an isolated propagating pulse. In general, however, an ultrafast laser source generates a train of pulses. A train of pulses is represented by, here we are showing intensity profile. Generally, when we represent a pulse, we just show like this. And what does it mean? It just we mean by drawing this, we actually try to show its intensity profile. If this is intensity profile, we should remember that actual electric field would be like following. Actual electric field would be in a different color. I'll present it. Actual electric field would be like this is the field envelope, and then field carrier wave would look like this. Carrier wave would be something like this. This is going to be the carrier wave. And so when quickly we are representing a pulse, we do not show all these oscillations. Generally we just show the intensity profile, and we should not get confused by looking at different representations. Now any ultrafast laser source will produce a train of pulses, and for train of pulses, if we have an observer sitting here, then what will happen, what I'll see as an observer, I'll see one pulse, then another pulse, then another pulse, then another pulse, then another pulse, and so on. They are coming to the observer. at a particular repetition rate. And why we get these repetition rates, we will be able to understand all these details when we will talk about the construction of ultrafast laser system. But what we have shown here so far is that the expression which we have written, Et equals At e to the power I omega average, I will write down omega average t minus again k average z. This is an expression I have represented. This is an isolated pulse propagating along the z direction. And how do I represent this pulse? The pictorial representation is not going to be like this. It is not like this. It is actually a field envelope which is At and then its carrier wave. Field envelope and its carrier wave. So this is the actual representation of this expression. Now this is representing one isolated propagating pulse. This equation doesn't represent a train of pulses. To represent train of pulses, we have to explicitly write down the expression for At, which we have shrink to At. There is an expression for the train of pulses. We have shrinked to At just because we used SVEA, slowly varying envelope approximation. But if we want to represent train of pulses, we have to get an explicit expression for the slowly varying component. Now, we note here that each pulse is represented by its intensity profile. This one, pulse 1, pulse 2, pulse 3, pulse 4, pulse 5 and so on. All these pulses are quickly represented by its intensity profile, not by its carrier wave oscillation. This just simplifies the representation, that's all. However, we must note that each pulse is nothing but a localized amplitude modulated electromagnetic wave, and that each pulse represents an amplitude modulated wave like the one which we have shown here. So each pulse is actually should look like this. One pulse, then another pulse, then another pulse, then another pulse, and like this way it should look like. And intensity, what does it right now? It is quite clear that what is intensity profile, what is field envelope profile, and what is carrier oscillation. We also should remember that when we talk about the pulse duration, we actually, what we mean, the pulse duration, this IT is intensity profile, then this this green color is going to be a field envelope function, and ET is this blue color is going to be, is in this picture, this blue color is representing the carrier wave. So this is carrier wave, which is the average frequency. Then this is intensity, and this is AT is the field envelope. And when we say that the pulse duration is delta t, we mean the full width half max of the intensity profile. We should remember this one. This intensity profile full width half max. It is not the full width half max of the field envelope. And if we have an intensity profile like this, which can be represented by e to the power minus 2at square that we have shown, then it is the full width half max is going to be delta t. And we remember that this is centered at t equals 0. Which means that at delta t by 2, at t equals delta t by 2, this time the intensity will drop down to half of its maximum value. Maximum value is here, I max. So delta t is related to its full width half max of the intensity profile, not of the field envelope profile. We have already seen that each pulse is characterized by its temporal width delta t, that is the full width half max of the intensity profile. In a train of pulses, repetition rate, how often these pulses are repeating for an observer sitting here, that repetition rate decides the separation between two nearest neighbor pulses. If TR is the repetition rate, then 1 by TR is the repetition time, which is represented by this. This temporal separation of neighboring pulses is the repetition time. Most of the ultrafast laser systems work at a repetition rate ranging from TR can range from 1 Hz to 1 megahertz. These are the options right now available. If W is the energy per pulse, which means the energy content for each pulse, how can I get that? If I direct this pulse to a power meter, then power meter, what it does, it gets an integrated intensity. Integrated intensity, time integrated intensity is nothing but the energy. How much energy content I have in each pulse, and if the total energy content each pulse having W, that can be expressed in joule, then we can define two quantities. One is peak power, that is nothing but energy which is localized within this delta T time scale. That is, the delta T is the full width half max of the intensity profile. So within that femtosecond time scale, how much energy I have concentrated. Another one is called average power. Average power is nothing but energy divided by repetition time. Repetition time is nothing but 1 by TR, which is where TR is the repetition rate. So these are the two important terminologies for the laser system. Peak power depends on the full width half max of the each intensity profile, which means that is the pulse duration of the pulses. It depends on the pulse duration. Delta T is the pulse duration. And average power depends on the repetition time. So let's say we have and these two quantities are, we often use these two quantities to define an ultrafast laser source. We can take a look at the technical specification of a commercially available ultrafast laser system, and now if we look at the technical specifications, we'll be able to understand what does it mean by each specification. Here we have taken an example of Spitfire AC, which is manufactured by Spectrophysics. There are many other vendors such as Coherent, KM Labs. They can also manufacture femtosecond laser system. We are just taking a look at the specification of Spectrophysics to get to know how to understand different specifications. So pulse width, the first specification is written here, pulse width 35 femtosecond. We know what does it mean. Pulse width, when we say pulse width 35 femtosecond, is the intensity profile, full width half max of the intensity profile. So this is my intensity profile, and 35 femtosecond is going to be full width half max of that profile. Repetition rate, we know, for an example, we can take this option 1 kilohertz, which means that I have each pulse coming at a particular rate, and the repetition time is going to be 1 millisecond. So in every 1 millisecond we are getting one pulse. That's why we have 1 kilohertz repetition rate. On the other hand, if we take the pulse energy, this option 5 millijoule energy, which means that W equals 5 millijoule. This is nothing but, if we direct the beam to a power meter, what does it do? It actually integrates the intensity over the time, and it gives me 5 millijoule energy. Power meter will give me 5 millijoule energy per pulse, each pulse containing 5 millijoule energy. And average power, there is an average power section here, and if we see that average power we can calculate, because we know P average is nothing but W divided by 1 by repetition rate, which is nothing but for this we have, for the specification we have selected, it is 5 millijoule per pulse energy divided by 1 by TR, which is nothing but 1 by 1000 second inverse Hertz, which gives me 5 joule per second, which is nothing but 5 watt. So this 5 watt is connected to 5 millijoule energy for a repetition rate 1 kilohertz repetition rate. So what does it mean? It means that in every 1 millisecond I will have one pulse coming out of this source, and this is and within this 1 millisecond time scale, I have been able to localize the energy, W amount of energy I have been able to localize. That's exactly what it means. And mostly in the experiments, average power will contribute to the total thermal heating. On the other hand, peak power will contribute to the nonlinear effects which we see during the propagation of the ultrafast pulse through the medium. So whatever we have seen so far is a spectrophysics Spitfire can produce a pulse as short as 35 femtosecond. Many other systems can be manufactured by Coherent and Chem Labs and many other vendors. Perhaps right now there are many vendors available. They can also produce similar short pulses. But one question is obvious right now. When you say that I have a pulse centered at 800 nanometer, this is my pulse spectrum, and the temporal width, this time domain representation is going to be here, and this is let's say 35 femtosecond. So this is the specification. Given this specification, one question is obvious: is there any limit of the shortest pulse duration which can be synthesized at a particular center wavelength? Let's say I have center wavelength 800 nanometers. When I say center wavelength, it doesn't mean that pulse is made of one single frequency component. It just suggests that center frequency component is nothing but the average frequency component. So I have many other frequency components present here. They all contribute, produce this constructive, destructive interferences, and then we get the pulse. But we name it with the help of center frequency component. We say that it is 800 nanometer pulse. Now question is, at the 800 nanometer pulse, if I try to reduce the pulse duration, then I definitely need more frequency component, because we know that time bandwidth product delta nu delta t is going to be constant. Okay, so in order to produce short pulse, I need, let's say, broad spectrum, broad delta nu. This delta lambda has to be long. Now, if I think of a situation that I have enough bandwidth to produce which will help me reduce the pulse duration. Question is, can I achieve the shortest duration pulse? What would be the shortest duration pulse I can achieve at 800 nanometer? So if in order to answer this question, we have to think about the oscillatory part. At 800 nanometer center frequency, I have these oscillations. Okay, and there are so many oscillations present in the 35 femtosecond pulse. 35 femtosecond, which means the intensity profile would be like this. The dotted line is representing the field envelope, and this would represent the intensity profile. And 35 femtosecond, it means that this width is 35 femtosecond. Now in 35 femtosecond, there are so many oscillations present. If I assume that I have been able to compress a pulse, which means I am reducing number of oscillations, and I am trying to compress a pulse. And if I compress a pulse, I can assume that in the end I may have only single oscillation present. I cannot imagine a pulse which is having less than one oscillation. I should have at least one oscillation in the pulse. Now if I have only one oscillation in the pulse at 800 nanometer, then I can find out the frequency for associated with 800 nanometer and the optical period. Frequency can be calculated very easily. C by lambda. C is 3 into 10 to the power 8 meter per second, and lambda is 800 nanometer. We can directly calculate it, and then from nu I can get the optical period. Optical period, what does it mean? This time scale from here to here. What is the optical period of the oscillation? One oscillation, how long does it take? And we see that at 800 nanometer center frequency, the optical period is going to be 2.7 femtosecond. What does it mean? It means that in order to sustain a pulse, the shortest duration pulse which I can produce at 800 nanometer is going to be 2.7 femtosecond. It cannot be less than 2.7 femtosecond, because if we make it less than 2.7 femtosecond, then we do not have one single oscillation even in the pulse, which is not possible. So it is quite clear that an ultrafast pulse at 800 nanometer center wavelength cannot be shorter than 2.7 femtosecond. In order to obtain a pulse shorter than 1 femtosecond, we need to shorten the wavelength itself, or optical cycle. This is why an attosecond pulse cannot be generated in near infrared or visible regime. What I need to do, if I want to reduce this pulse duration further here, what I need to reduce the optical cycle, which means I can reduce the instead of this long optical cycle, I have to use this short optical cycle. And short optical cycle means you have lambda which is much less than 800 nanometer. I have to reduce the lambda. So I have to go for the X-ray regime. So attosecond pulse can be produced only in the extreme ultraviolet or X-ray regime of electromagnetic radiation. It cannot be produced in the visible range or the near IR, because of optical cycles are too long for attosecond pulses. We have already seen that a pulse with center wavelength 800 nanometer exhibits optical period of 2.7 femtosecond. On the other hand, pulse duration is represented by the full width half-max of the intensity profile. Duration of a typical ultrafast pulse, which is frequently used in the lab measurements, is, let's say, 100 femtosecond. So we have seen that this oscillation period is at 800 nanometer. This oscillation period is 2.7 femtosecond. This is why in a 35 femtosecond pulse, I have 35 femtosecond is the full width half-max of the intensity profile. So in 35 femtosecond pulse, I have many such oscillations present in the pulse. And 2.7 femtosecond is the minimum oscillation I should have. On the other hand, the pulse duration is 35 femtosecond. So both oscillation as well as the time by which this envelope function is changing, both are too short, too fast with respect to any electronics. Within this time scale, intensity profile variation occurs. Within this 35 femtosecond, intensity variation occurs, but response time of all time sensitive detectors such as photodiode, photomultiplier tube, CCD camera, etc. is mostly nanosecond. So if we look at this time scale and compare with the response time of electronics, it is going to be nanosecond, which is 10 to the power minus 9 second, and these are femtosecond 10 to the power minus 15 second. They are way too fast as compared to the time scale response time of electronics. Therefore, time sensitive detectors are way too slow to measure optical cycles. Optical cycles cannot be measured, as well as we cannot measure the intensity profile as well with the help of time sensitive detectors such as photomultiplier tube, CCD camera, photodiode, etc. Available time sensitive detectors are way too slow to measure the ultrafast intensity profile and field and oscillation. They can only measure, because they are slow, they can only measure time integrated intensity. This is nothing but what they will measure. It's more like when you look at a rotating fan, our eye is too slow to capture every blade of the fan, and what we get a blur image, and that blur image mathematically will be represented by a time integrated signal which is given by this, and this is nothing but closely related to energy per pulse, energy content of the pulse, energy per pulse, which is nothing but time integrated intensity. We'll stop here and we'll continue this module in our next lecture.